Alright, ladies and gentlemen, to begin this video, I have a confession to make. For years, we've talked about how things are soluble or insoluble. As it turns out, it's not the case. Really, everything's soluble. It's just a matter of how soluble it actually is. And to gauge how soluble something is, we use what's called the solubility product constant, or KSP. That K, it's the equilibrium K. We're just dropping the SP down there because we're talking about the solubility product. So things that dissolve, ionic compounds at least, something like calcium carbonate, which we know is insoluble, quote unquote. But in all actuality, it does dissolve. It's just that the concentration of Ca2 plus and CO3 2 minus is so small that we consider it insoluble. Same thing with lead chloride, so it breaks apart into Pb2 plus and then 2 Cl minuses, so its KSP would be this concentration of Pb2 plus times the concentration of Cl squared. Both of these are going to have KSPs that range between 1 times 10 to the negative third to 1 times 10 to the negative 54th. So what that means then is that they are very, very small numbers. So the concentrations of both of these are going to be so tiny that it doesn't really matter. And remember, in equilibrium questions, we never put the solid state inside of the expression. That's why the KSP for these reactions is just going to be the cation times the anion. And of course, you raise it to the power, so since there's 2 Cl's produced, because it's PbCl2, it would be the concentration of Pb times the concentration of Cl squared. So if we were to look at KSP values for both of these, we would see for calcium carbonate it's 8.7 times 10 to the negative ninth, and for lead chloride it's 1.6 times 10 to the negative fifth. Both of these are at 25 degrees Celsius. Remembering that concentrations or solubility changes with temperature, so this is locked into a particular temperature. And if we ask the question then, which of these is least soluble, so which one will dissolve the least if we put it in water? Well, we'd look at both of these values, and if we take a look at this one, it's a much, much smaller number, because written out it's 8,7 with 8 zeros in front of it, whereas lead chloride is just 4 zeros in front. And so we can see that this number is smaller, therefore it is least soluble in water. This is less soluble in water than lead chloride is. And that's because the total number of ions of calcium 2 plus and carbonate CO3 2 minus multiplied by each other, so the product of those two is less than the product of the lead ions times the chloride ions. And of course, the reaction also tells us the ratio of the different ions. So we can see from lead chloride that lead 2 plus only has one of those, whereas chloride has 2. That means for every 1 lead in the solution, there will be 2 chlorides. Or another way of thinking of that, there will be half as many chlorides as there is leads. So then for every 1 mole of lead chloride that we put in water that dissolves, you're going to produce 1 mole of Pb2 plus and 2 moles of Cl minus. So it's a 1 to 1 to 2 ratio. Alright, so let's practice with this. The solubility product constant for lead 2 fluoride is 3.6 times 10 to the negative 8th, and that's at 25 degrees Celsius. Keep in mind, they don't refer to this as equilibrium, but that's exactly what it is. They call it the solubility product constant, but just remember when you see this term right here, what they're referring to is KSP. So solubility product constant is KSP. And here are the steps that we're going to go through to solve this. Some important terminology right here is this word molar solubility. So molar solubility is something you're going to see a lot in this, and all that is just how many moles will dissolve per liter. And so what we're looking for there is moles per liter that has dissolved. So here is where it is helpful to know your ions and your charges. So in this case, lead 2 fluoride, that's going to be PbF2. And we're talking about the solubility product, so we need to put an equilibrium arrow in there. And that's going to break apart into Pb2 plus and then 2 F minuses. So for every 1 lead fluoride, we're going to produce 1 lead ion and 2 fluoride ions. Second step then is to write the equilibrium expression. Equilibrium in this case is the solubility product constant, so KSP. And we're just putting the numbers, or we're just putting the units in here. And so it's going to be Pb2 plus times F minus, and that's going to be squared since there's 2 of them. There is no reactants, and so it's just products over nothing or over 1. And so this would be our complete equilibrium expression. All right, let's go ahead and ice this real quick. So I'm going to move that out of our way. And we can put our little ice table underneath these guys. So initially we're going to have 0 lead and 0 fluoride. So this is when we first drop the solid in there. Hasn't had time to dissolve, but then a change is going to happen. And so our lead fluoride is actually going to dissolve, so it's going to disappear by, we'll say, S amount. So instead of X, we'll use S. And then that means the lead ions are going to increase by S. So this is going to break apart by S amount, and so that's going to increase by S amount. It's a 1-to-1 ratio. Fluoride, on the other hand, is going to increase by 2S. So for every certain amount that this dissolves, we're going to get 2 of those. So if 4 lead fluorides dissolve, we would produce 8 fluorides, and we would produce 4 leads. So then another way of saying our KSP equation is to say that S times 2S, and of course, since this is a 2 right there, and since we have a squared on our equation right there, we are going to need to square this right here. So KSP would be equal to S times 2S squared. The nice thing about these S values right here is they are guaranteed to be identical. If this dissolves by 4, we're going to make 4 of those, and we're going to make 2 times 4 of those right there. So if this number is 8, that number is 8. If this one is 1,000, that one is 1,000. The S values are always identical because they come from the exact same thing. So we can reduce this equation or combine it so that KSP is equal to 4S squared. So that's just taking this square and distributing it out, and then multiplying by that guy. I'm sorry, not 4S squared, that'd be 4S cubed. And multiplying those two S's by each other. And so now we know the KSP value, so we can move some things around here, and we can go ahead and solve. So KSP we saw in the question was 3.6 times 10 to the negative 8th, and that is going to be equal to 4S cubed. And so we can solve this by first dividing both sides by 4 and then taking the cube root of our problem, and that's going to give us an S value of 2.1 times 10 to the negative 3rd. Alright, so S, this little unit S, there's a reason we use that, and that's because what S represents is the molar solubility. So when the question asks us to find the molar solubility, what they really wanted to find was S, or that's what we recognize it as. So the molar solubility of lead fluoride then is 2.1 times 10 to the negative 3rd moles per liter. So that means for every liter of solution, it's going to dissolve by 2.1 times 10 to the negative 3rd moles. And so then at equilibrium, or once it's dissolved in a saturated solution, the concentration of lead 2+ is going to be 2.1 times 10 to the negative 3rd, because for every one that dissolves, we produce 1 of those. So it's going to be the same. And then the concentration of the fluoride ions, since we're going to produce 2 of those in solution, would just be 2 times S. And so in the case of this question, that would be 4.2 times 10 to the negative 3rd. And both of these are molarity, or moles per liter. Okay, so when we were talking about saturated solutions, what that means is we are at equilibrium. So a solution is at equilibrium when it is saturated. That means you have a little bit of solid left at the bottom, and they're dissolving, undissolving in this kind of constant rotation. And so it looks like this, just when we get our solid down here, and some of it's going to dissolve, and as that dissolves, it's going to take up room, so other stuff is going to undissolve and precipitate out. But the same amount of solid stays at the bottom, and the same concentration stay up here, as long as it is at the same temperature. And so you can't do KSP problems unless you have a system that is saturated. Because if it's not saturated, you won't produce this solid at the bottom, and you will not set up an equilibrium.